just one quick counterexample to show you why the star domain is important. Okay, so actually it's an example that we will use later on. So let's write this. So important example. If you remember earlier this year, well, if you don't remember, that doesn't matter. But we had at some point this vector field minus y over x2 plus y2 and x over x2 plus y2. First thing that we have to see is that the domain of V is, well, R2 star. I must exclude the origin because otherwise it would just mean the dividing by 0 my two components. Okay, so the domain of V is R2 star. That's the first domain that comes naturally. If you compute so that's what was called the P, that's what was called the Q. If we compute dP over dy, what are we going to get? That's just going to be -1 times x2 plus y2 plus y times 2y times this divided by x2 plus y2 the whole stuff square. So this is just going to give me 2y square minus y square, so that's y square minus x square over x2 plus y2 square. If you compute dq over dx, so do it at the same time as I'm doing it, I'll pause the video. So that's just going to be, well, you get something very similar. So 1 times x2 plus y2 minus x times 2x and divided by x2 plus y2 square. So that's again the same stuff, y2 minus x2 plus y2 square. Okay, so this property is satisfied, and actually you can try to find the original scalar potential. Let's just give you actually that V is equal to the gradient of arctangent of y over x. That's not an easy one, I agree. Okay, so it does come from a scalar potential, but there are some steps that are not going to work for us because it's not a star domain. Okay, so keep that in mind. So dv like this, when I choose R2 star, is not a star domain, but if I use a second, let's call that d prime v, R2 star, well, sorry, R2 star minus or minus, okay, so the one without the negative real line. So that would be xy such that x is greater than 0, xy in R2. Well, let's choose that. Let's choose R2 plus, just the half plane. Okay, greater than 0, that's going to be a star domain. Okay, so let's keep this example in mind for later on when we will do some further calculations. Okay, this being said, let's compute. That's the important part. Well, it was also important before, but circulation of a conservative vector field. Okay, so let's assume that we have our curve gamma, which is described by gamma of t for t in, let's say, t0 capital T, all right? The curve of class C1, by this I mean gamma is C1, I mean that x of t and y of t are both C1 functions. Okay. Now let's say that my vector field V is actually made out of df over dx and df over dy. So that is obviously a conservative vector field. So what do I get when I want to write the line integral on gamma of my vector field? So integral on gamma of df over dx plus df over dy. Okay, using the previous calculations that we did earlier. So that's just going to be the integral between t0 and capital T of df over dx of x of t, y of t, times, you remember, x prime of t plus df over dy, x of t, y of t, times y prime of t, the whole stuff, times dt. But maybe you have observed that we have something very peculiar here. We have df over dx x prime plus df over dy y prime. That's exactly the chain rule. Okay, that is exactly the chain rule when I want to do d over dt of f of x of t, y of t. Okay, this is an example we did many times. So in the end, what do I get? I get that this integral is going to be, well, the integral between t0 and capital T of d over dt of f of x of t, y of t, times dt. So you know that the integral of the derivative is just a function, so that's going to be f of x of t, y of t, so t0 capital T, and that's just going to be, well, the value of f at x of capital T, y of capital T, minus the value of f of x of t0, y of t0. Okay, so what is the important moral of this story? Okay, the circulation, well, it's very important. The circulation of a gradient field, conservative vector field, conservative vector field, okay, depends only on the values of, well, the potential it comes from, so let's call that f, at the bounds of the curve. That means it doesn't mind what path you use to go from that x of t0, y of t0, that's x of capital T, y of capital T. Doesn't matter what convolutions you did in between. In the end, if you want to calculate the circulation of this gradient field, of a gradient field on that curve, it's just going to depend on the value at the bound. So it would be exactly like if you had gone there and using a straight line. Okay, and that works as long as your curve is included in a star domain.